Hey guys, good morning, afternoon, evening, midnight. We don't know, but we're glad to see you. This is lesson 9.5, complex numbers, and I never can pronounce this right. DeMoivre's. It's French, so who knows? Theorem. We'll call it DeMoivre's theorem. I think the V is silent. We're going to go with that. The objective of this is to convert complex numbers from rectangular to polar form and vice versa. So that's what we're going to do. Not real hard. Complex numbers are part real number and part imaginary number. So think of like when you have a mixed number, for instance, maybe I have 2 1/4. Okay. So that is what we have, a whole number and a fraction. So when I have a complex number might look like 2 plus 3i, where we have a real part and we have an imaginary part. So it's a little bit of a mixture for the number. The basic form of a complex number is a plus bi. So a is your real part, and the bi is your imaginary part. And then don't forget that I is actually the square root of -1, and it's imaginary because, well, in reality, we cannot take the square root of -1. Okay, let's talk about absolute value of a complex number. It says the absolute value of a complex number is the distance of the point representing the complex number from the origin to its location in the complex number. Little interruption there. But anyway, it's just the distance. The point is, the complex number is from the origin in the complex plane. So that's what absolute value is. It's just like absolute value of any number is the distance it is from 0 on the number line. Okay, so we're actually going to use that value to help us out here going from rectangular to polar. So first we're going to let z equal a plus bi. So we're going to let z be our complex number. And so this is just saying, hey, we're going to take the absolute value of that complex number. And what it then looks like is the square root of a squared plus b squared. So we take that complex part, a plus bi. And so the a value, our real number, is going to be squared. And then the coefficient on the imaginary is going to be squared. And that's how we find the absolute value. Okay, we'll see how that works out here with polar form in a minute. Okay, so for complex numbers, we have, or for polar form of complex numbers, we have z equals a plus bi. And that's our complex number. So if we want to change that to polar form, then it's going to look like this, where that z, which is our a plus bi, is equal to r, the radius, times cosine theta plus I sine theta. To find out what our r is, we're going to use that square root of a squared plus b squared, which is really the absolute value of our a and b, or of the complex number. And then depending on whether a is greater than 0 or a is less than 0, we're going to use one of these, tan inverse of b over a to get theta, or tan inverse of b over a plus pi to get theta. It just depends on what a is, whether it's really positive or negative here. So in the first problem, we're going to just kind of walk through how to do, to take one of these complex numbers and put it in polar form. So remember, it's a plus bi, and we have 4 plus 4i. So that means that a is 4 and b is 4. Our equations then in the polar form is r times cosine theta plus I sine theta. Just did a little double check, make sure I didn't write it down wrong. So r was the square root of a squared plus b squared. So we're going to do that. We've got the square root of 4 squared plus another 4 squared, which is the square root of 32, which is 4 square root of 2. So that's our r. And then a is greater than 0, so I'm going to use the form theta is equal to the tan inverse of b over a. So we've got the tan inverse of 4 over 4. So that's the tan inverse of 1. So I'll do that real quick. And that's 45 degrees, or pi over 4, which is theta. Okay, now I can substitute all that back in to the equation, or the polar form. And I'm going to get r, which is 4 square root of 2 times cosine of pi over 4 plus I sine of pi over 4. And there's my polar form right there. Okay, so what we can really use this polar form for, obviously we can take an imaginary number and write it in polar form, but we can actually use that concept to take an original complex number and take it to a power, okay? Instead of, and we can take it to fairly high powers quickly, okay? And this is what I say, DeMoivre's theorem. It says that if z, which is my complex number, is written as r times cosine theta plus I sine theta, then by its theorem, I'm going to forget that little d there. By its theorem, if I take z to the n, so whatever that complex number is to some n power, then I can take the polar form and I'm going to raise r to the n, and I'm going to take cosine of n times theta and sine of n times theta. So I'm going to put an n in there. And you'll see how this works to help us in a quick way take a complex number, for instance, square root of 3 plus I to the 7th power, without having to expand it and take square root of 3 plus I times square root of 3 plus I times square root of 3 plus I, and you get the idea. So we're going to make this a little quicker. All right, so my a is square root of 3. My b, because this is just I, would be 1 then. And my n, to use in the theorem, is 7. So that means the square root of 3 plus I to the 7th is equal to r to the 7th times cosine of 7 theta plus I sine of 7 theta. Okay, so I need to figure out what's r and what's theta in this problem. We know that r is the square root of a squared plus b squared, so we'll use that. That's the square root of 3 squared plus 1 squared, which is the square root of 4, or 2. And then for theta, we're going to use the tan inverse of b over a, because a is greater than 0. And so that's the tan inverse. That's the tan inverse of 1 over the square root of 3, or square root of 3 over 3. which is pi over 6. Okay, so what we'll do is we'll plug the r and the theta into the polar form, and then we're going to simplify it. Okay, so we'll have r, which is 2 to the 7th, times the cosine of 7 times pi over 6, plus I times sine of 7 times pi over 6. Okay, so that's going to give me 128, and that's the cosine of 7 pi over 6, plus I times the sine of 7 pi over 6. And so we've gone from our rectangular form to a polar form, and then we're going to go back to that its value. Okay, how much is that? So back to a rectangular form. So that's 128. Cosine of 7 pi over 6. Its value would be negative square root of 3 over 2. And the sine of 7 pi over 6 would be 1/2, or negative 1/2. So that's going to be minus 1/2 I. And then we'll just distribute. Okay. So we're going to distribute the 128. And when we do that, we're going to get negative 64 square root of 3 minus 64i. And that right there is equivalent to the square root of 3 plus I to the 7th. So you could see how that makes it a whole lot easier. Instead of trying to multiply it out by all the time, we can just use that theorem. Okay, so I'm hoping pretty simple set of notes here. We went from a rectangular form or a complex number to a polar form. We talked about the absolute value of a complex number, and then we took a complex number to a power. All right, you guys got any questions, please message me, let me know, and I'm happy to help you, okay? And there'll be an assignment attached.